Finally, the video about the Wobbulator coil tester that I developed during the past weeks. Took me quite a long time, but anyway. Here is the front of the unit. What do we see here? We see a horizontal line shift. We see here the orange knob that's necessary to set the frequency, and we have here 3 outputs. One goes to the coil and the test, so the unknown coil, that's here now at the moment. And here we have the ground and mass that go to the horizontal deflection of the oscilloscope, and this is the vertical deflection. And here we can set the sweep frequency. So, the schematic at first. Looks a little bit complicated, but is not very complicated in fact. How it works is this: we have a sawtooth generator that sends out a sawtooth in the order of approximately 8 volts. That goes to an unknown coil. There are 2 diodes paralleled here. So here are 2 diodes paralleled. I have not used a real varactor, variable capacitor that can be driven via a voltage, but only 2 simple 1N5408 diodes. They are paralleled, anti-parallel, but they together parallel the unknown coil. It means that the oscillator starts to oscillate on a certain frequency when that coil is healthy and when it works nice. It has a certain resonance and it has a certain resonance peak. And that means that the frequency wobbles around the frequency of that coil in the order of 20 Hertz up to 40 Hertz. Here's the oscillator made with a field effect transistor. There was already an earlier video about it. So that wobbling radio signal, say on 8 MHz or so, is sent out here to a 1 transistor amplifier. It is rectified, and that means that we have an output signal that we can send to the vertical plates of the oscilloscope. So you need an oscilloscope that you can set to the so-called XI mode, X horizontal, I vertical, and that you can say send the sawtooth wave into the horizontal plates and the signal coming out of the wobbulator to the vertical plates. So that's what's happening here. And then we see the resonance peak of the coil. Before I forget it, let me show the detector. This is the detector, very simple. It was already in an earlier video. This is the oscillating coil. The signal is sent to a Darlington that amplifies and makes that LED here, fierce red LED, light up. And of course it's necessary because when there is no oscillation, you see something on the screen, but it can mean that there is no signal. So in fact you are looking at nothing. So here is that red LED that shows that the circuit oscillates. Here you can also see via the scope that it oscillates. But when you don't have 3 oscilloscopes, you can only use that, say, red LED as an indicator that the circuit works. Here we see the resonance of this coil, and you can conclude that this very simple looking coil here is a good quality coil. It has enough quality to make the oscillator work on 11.8, say 12 megahertz, and it's only, say, 6 windings or so. So that gives you a good indication where the coil works. So let's try to change the frequency a little bit by turning this. Let's see what happens. So here the coil does not perform okay. There is still oscillation here, and we see here also there is still oscillation, but the coil doesn't perform good, and also the counter gets unstable because it does not get enough signal. So we go back to the, so here is say the best frequency where it works, 12 megahertz. I now stick into that coil a ferrite rod. That means, of course, when we look at the radio theory, that the frequency will go down. And let's see where the coil now performs. We see an enormous oscillation. I have to change the scope a little bit. We see also an enormous peak here. So here, and let's again change here the frequency a little bit. We see the peak go up, and here it goes down again. So here there is the maximum performance of this coil, and we are on 8.6 megahertz. This hinders a little bit, 8.6 megahertz. So this is a way to test radio coils, and I've made it in such a way that the circuit works from approximately 350 kilohertz up to 12 megahertz. Perhaps with higher quality coils, with silvered wire for instance, perhaps you can get a little bit higher, but 12 megahertz is more or less the highest frequency where this can work. So, show the function of the sweep frequency. Here the sweep is low, approximately 20 Hertz. Here we go to say 50 or 60 Hertz. Makes it somewhat better visible. Here the blue is the amplification factor of the one transistor amplifier. This must also be set to a certain maximum where it performs best. There is a switch for auto, manual, auto and manual. Auto means that it is connected to the sawtooth generator. Manual, that you can say give it by hand a certain voltage. I don't want to elaborate on that. There are two switches here, and both are responsible for the working point, say the bias of the oscillator, and that is say a thing to tell something about. These two switches are here, switch 2A, and here we have switch 2B, and they must set in such a way that the oscillator oscillates, and it means that on certain positions it works best for lower frequencies, and on other positions it works best for higher frequencies. Say you must do that experimentally. Say play a little bit with these switches. We'll try to demonstrate it. So for instance here you see what happens, and perhaps I can even now switch it off. Because these two capacitors form a capacitive voltage divider that is responsible for the oscillation. And it also means, and that's perhaps a small flaw of the circuit, that when you set these switches to different positions, the resonant frequency can change a little bit. I hope I can demonstrate it. Well, that's something, say, to do experiments with and to get insight. That's the most important thing. The circuit can help you to give insight. Let's look at the back side. Here is say the oscillator part, that's here. And here is the sawtooth generator. I don't want to use a screwdriver to point things on, but here is the sawtooth generator, here is the oscillator, and this is of course the power supply. Very simple, made with a 7812 chip. So that's more or less all to tell. Back to the schematic. I think that's the most important thing. Everything was tuned and tested, and for instance, what was critical? For instance, this resistor that is at the AM detector. At first it was 200 kilo ohm, but with 47 kilo ohm I had better results. So, thanks for watching.